Oh, there. So we've gone over improper integrals with infinite domains and improper integrals where the function has a vertical asymptote, okay, or discontinuity. So now we're going to look at a few more examples just to get some practice with the method. Okay, so the first example is the integral from minus infinity to 0 of 1 over 3 minus 4x dx. Okay, so we already see that we've got a minus infinity at the bottom here. Okay, so it's one of those infinite domain integrals, but we should also be careful about looking at this denominator here. So if we take a look at this denominator, could it be 0 on this interval here? If it could be 0, then we know that we're going to have a 1 over 0 situation, and that's going to go up to infinity. So let's just check. So we're going to check for the denominator being 0. Okay, so in this case, we're going to have 3 minus 4x is equal to 0. So 3 is equal to 4x. So x is equal to 3 over 4. Okay, so when x is equal to 3 over 4, we've got ourselves a vertical asymptote. But notice that on our domain here, we're going from minus infinity to 0. Okay, so that's not going to be a problem for us. But we still have an infinite domain to worry about. Okay, so we can write this as the limit as t goes to minus infinity of the integral from t to 0, 1 over 3 minus 4x dx. Okay, so we can integrate this. This is going to be the limit as t goes to minus infinity of minus 1 over 4, the natural log of 3 minus 4x. Okay, and we're going upper bound 0, lower bound t. Now we can substitute the bounds, so we get a function of t, and then we take the limit. So this is equal to the limit as t goes to minus infinity of, if we substitute 0, we're going to get minus 1/4, the natural log of just 3. And then minus and minus, that's going to be plus 1/4, the natural log absolute value, 3 minus 4t. Okay, so now we're taking the limit as t goes to minus infinity. Okay, so the limit doesn't care about that constant that we have. So it's going to be minus 1 over 4 natural log of 3 plus 1/4, the limit as t goes to minus infinity, natural log of 3 minus 4t. Okay, so as t goes to minus infinity, we see that this inside part of the log is going to go to plus infinity. Okay, because it will end up being 3 plus infinity there. Now, the natural log of infinity, well, that just goes off to infinity. Okay, it's unbounded. In other words, the second part here, that is divergence. It goes to infinity. So it doesn't matter what this first bit is, because the second bit is infinity, the whole integral diverges. So the integral diverges. Okay, which means we can't write down a nice finite value for this integral. Okay, let's have a look at another example. Example 2, we have the integral from 0 to infinity sine squared of x dx. Okay, again, we've got this infinite integral here, okay, with the upper bound being infinity. Now, sine squared of x doesn't have any asymptotes. It's a nice continuous function, so we don't have to worry about that. Okay, but we do have to worry about that infinity. So this is going to be the limit as t goes to infinity of the integral from 0 to t sine squared x dx. Okay, so we can calculate the integral and then we can take the limit and see if it's finite or not. So this is going to be the limit as t goes to infinity of, well, we can integrate this by changing it to something with cos, using that angle formula, the half angle formula. So this is going to be 1/2 1 minus cos 2x dx. Okay, so this we can integrate. So this is going to be the limit as t goes to infinity of, we're going to have 1/2 x minus 1/4 sine 2x, okay, from 0 to t. Okay, so now we can substitute t, we can substitute 0 and see what we get. So this is going to be the limit as t goes to infinity of 1/2 t minus 1/4 sine 2t. Okay, if we substitute 0, we're just going to get 0. Now, what happens when we substitute, not when we substitute, when we take the limit as t goes to infinity? Well, this first term, half of t, it doesn't matter what we scale it by, half of infinity is still going to be infinity. So this first term diverges. Okay, so already the limit diverges. We don't even need to look at the second term. But let's just look at it anyway. So I'll put a little star here. What happens when t goes to infinity with a trig function that just oscillates? So if we take a look at this function, sine 2t, and it works for any trig function, sine 2t, cos of t, anything like that, it's going to do something like this. Okay, it's just going to oscillate back and forth between -1 and 1. In other words, as t goes on to infinity, it's still going to oscillate back and forth. In other words, it never settles on a value as t goes to infinity. So this function never settles on a constant value. Now, because it doesn't settle at a constant value, it also diverges. Okay, so it may not go to infinity or minus infinity in the usual sense that we say something diverges. However, it's not convergent. So it never goes to some fixed value when t goes to infinity. So if anything doesn't converge, we say that it diverges. Okay, so it doesn't go to infinity, but it still diverges. Okay, so that's an important thing to keep in mind. Okay, divergent doesn't only mean goes to infinity. Okay, so both terms diverge. So we say that the limit doesn't exist, and so the integral diverges. Okay, so we don't have a nice finite value for this integral. Okay, let's have a look at another example. Okay, example 3. We have the integral from 1 to infinity, the natural log of x over x squared. Okay, so we want to work this out. Now, let's just check if there's any asymptotes. So x squared at the bottom, that's nice and continuous. There's no problems there. The natural log of x, there is a problem when x goes to 0, but our lower bound is 1. So we don't have a problem with that. Yeah, so everything should be fine. However, we do have a problem with this upper bound being infinity. Okay, we need to worry about that. So this is going to be the limit as t goes to infinity of the integral from 1 to t, the natural log of x over x squared dx. Okay, so we need to try and figure this out. Now we've got the natural log of x at the top, and we've got something with x at the bottom. That calls for a u substitution, because we know that the derivative of the natural log is 1 over x. Okay, so that gives us one of the factors in the bottom there. So if u is equal to the natural log of x, then du is going to be 1 over x dx. Okay, but we still need that extra factor of 1 over x. So e to the u is going to be x. So e to the minus u is 1 over x. Okay, so that gives us everything we need now. So this becomes the limit as t goes to infinity, the integral. Now we need to change the bounds. So when x is equal to 1, u is equal to 0. When x is equal to t, u is equal to the natural log of t. Okay, so that's fine. Then the natural log of x, that's going to be u. The 1 over x that we need, that's going to be e to the minus u. And then that other 1 over x dx, that gets replaced with du. Okay, so now we've got an integral in terms of u to solve. So this is going to be equal to the limit as t goes to infinity, the integral, and then we have the integral from 0 to the natural log of t, u e to the minus u du. Okay, so I just put that in brackets because I hope you can see what's coming next. We've got a product of two things here. So we are going to have to use integration by parts. Okay, so this is going to be equal to the limit as t goes to infinity of, so we need uv, so that's going to be u minus u e to the minus u from 0 to the natural log of t minus the integral from 0 to the natural log of t. And then remember, this was that v du part, so it's going to be minus e to the minus u du. Okay, so that's just using our integration by parts. So let's substitute, do that last integral, and then finally we can take the limit. So this is going to be the limit as t goes to infinity of, if we substitute the natural log of t, we're going to get minus the natural log of t times e to the minus natural log of t. Okay. And then we have plus the integral from 0 to the natural log of t e to the minus u du. Okay, so a bit more work to do. So this is going to be the limit as t goes to infinity of minus the natural log of t and e to the minus natural log of t, that's 1 over t. So we have minus 1 over t with the natural log of t at the top. Something like that. Plus, and then we integrate this again. So we have minus e to the u going from 0 to the natural log of t. Okay, so let's substitute. So we're going to get the limit as t goes to infinity of minus the natural log of t over t plus, and then we're going to get minus, sorry, there's a minus there. We're going to get minus e to the minus natural log of t, and then minus and minus make a plus, and then we're just going to get plus 1 if we substitute 0. Okay, so what do we get? We're going to get the limit as t goes to infinity of minus the natural log of t over t. Then we're going to get minus 1 over t plus 1. Now, what happens when we take the limit as t goes to infinity? Well, with this first term, the top part's going to be infinity, the bottom part's going to be infinity, so that's an indeterminate form. So if we want to find the limit, we have to do a bit more work on that. So let's just circle this and take it to the side where we need to do a bit more work. So that's going to be minus the natural log of t over t. Okay, we need to work that out. However, 1 over t, that's just going to go to 0. That's pretty simple. So that one's going to go to 0, and the 1 is left over. Okay, we don't want to forget about that. Okay, so how do we handle this? Well, we need to use L'Hopital's rule because we've got infinity over infinity, got a differentiable function at the top and at the bottom. We can take the derivative. So we're going to have minus 1 over t at the top, and at the bottom, it's just going to be 1. And if we take the limits, this is just going to go to 0. So altogether, we get 1. In other words, the integral converges. Yeah, and it converges to the nice finite value of 1. Okay, I think that's enough examples for today. Let me leave you with some homework problems to try. Okay, maybe 5. I think that's good for homework. So for the first one, we have the integral from 1 to infinity of x plus 1 over x squared plus 2x dx. So we've got ourselves a rational function. So that means we need to be using partial fractions, but also we have that the upper bound is infinity. Okay, so we're mixing things together here. We need to be using partial fractions for the integration, and remember to use a limit for the upper bound. Okay, number 2. Let's have the integral from minus infinity to 0 of x over x to the 4 plus 4 dx. Okay. Number 3, let's have the integral from 0 to infinity of sine theta e to the cos theta d theta. Okay, that's a bit of a weird one, but just note the upper bound being infinity there. Number 4. We have the integral from 0 to infinity of 1 over x squared plus 3x plus 2. Okay, just keep in mind that that denominator could be 0. You're going to have to check that. And then that would give us asymptotes if that denominator is 0. Okay, last one here. We have the integral okay, let's say the integral from 0 to 3 of 1 over x squared, sorry, that's an x squared, minus 6x plus 5. Okay, so again, check that denominator. There could be some vertical asymptotes there. Okay, so these are the homework problems for today. Some of them with infinite bounds, some of them with asymptotes, and then this number 4, it might have both, might have infinite bounds and an asymptote. You're going to have to check. Okay, so you can post these on the class WhatsApp group, okay, if you want to verify your solutions. And if you are the first one to post a correct solution, you get bonus points for either the summative assessment we've got coming up or test 3. Okay, so I'm going to divide the bonus marks wherever they will be used best. So maybe your summative quiz was not so good, but your test 3 was really good, then I'll put your bonus marks to that. Okay, just so that you get the most out of them. Okay, but as always, if you have any questions, feel free to email me anytime you like, or you can post your questions on the WhatsApp group. Okay, I will see you on Monday for the remaining section on improper integrals, and that is the comparison test. So just a little preview of that. If we have an integral that we can't integrate directly, okay, maybe it's too difficult, or maybe you actually can't do it, okay, maybe there isn't an antiderivative, then what we can do is we can compare that integral to another integral that we can solve. And then through this comparison, we can see if our more difficult integral converges or not, okay, by comparing it to another integral. Okay, so we will be doing that on Monday. And then after that, we will look at the new section on finding the length of curves. Okay, there's a nice formula for that, and we'll look at some examples. Okay, but if you do have any questions, please let me know.